Hey guys, this is Carrie, and this is the answer key to this problem, or this question, or this homework set. Sorry, this is my fourth time shooting this video now because my iPad kept having errors. So let's see if it works this time. There's a correction that was made to the problem. Lowercase t is the time in hours since the turkey is put in the oven. Alright. After sitting out of the refrigerator for a while, a turkey at room temperature, 68 degrees Fahrenheit. So this is the initial temperature of the turkey, is placed in an oven at 8 a.m. When the oven temperature is 325 degrees Fahrenheit, Newton's law of heating explains that the temperature of the turkey will increase proportionally to the difference between the temperature of the turkey and the temperature of the oven as given by the formula below. You don't need to know anything here. They gave you the formula, so you don't need to construct it. This is going to be awesome for us. It's a complicated looking formula, but I bet we can figure it out based on the meaning of these things. T sub A is the temperature of the surrounding object. So the object that's changing temperature in this problem is the turkey. The temperature surrounding the object, well, when we put the turkey in the oven, the temperature surrounding the turkey is just going to be the oven temperature. And we actually know the oven temperature. The oven temperature is 325 degrees. So throughout this problem, T sub A will always be 325 degrees. Next up, T sub 0 is the initial temperature of the turkey, and that was given to us too. We know that this T sub 0 will always equal 68 degrees Fahrenheit. Little t, the time in hours since the turkey is put in the oven, this is going to be changing in this problem, depending on which time we're looking at. Big T, the temperature of the object, that's also going to be changing, because the turkey is going to be warming up to oven temperature over time. Little k, the decay constant, that was not given to us. The turkey reaches the temperature of approximately 100 degrees Fahrenheit. So they're actually given some new information here. This looks like big T and little t. Find the value of k. That sounds like part 1 of this problem. We're going to be rounding that to the nearest thousandth. Write an equation to determine the value of the turkey after t hours. This looks like a new part to the problem, so we'll call that part B. Hey. Lastly, determine the Fahrenheit temperature of the turkey to the nearest degree at 3 p.m. Someone's going to fill their water bottle, so it's going to sound like peeing again. I hope you guys heard that in the last video, but this is someone filling their water bottle in the staff room. Sorry, you can't control the background noise. Finally, determine the Fahrenheit temperature of the turkey to 3 p.m. So this is part C. So let's take a look at part A. Part A says the turkey reaches the temperature. Part A says we're trying to find the value of K. So let's go to our formula. Our formula says big T, that's 100 degrees Fahrenheit for this part, is equal to T sub A. That's always 325, we knew that from before, the temperature of the oven, plus T0, the initial temperature of the turkey, minus the oven temperature, 325, equals e to the negative k times our t value, which is 2. So I'm starting to get a lot of scratch work over this problem, but now we have an equation that we can just solve, so we don't even have to worry about the words. Let's subtract 325 on both sides. That becomes negative 225 equals, simplifying this part too, that becomes negative 257, e to the negative 2k. Next up, we divide by negative 257 on both sides. That gives us, let's see, I don't have this part worked out. Actually, you know what? I don't want to go to Desmos yet. I'm going to do all the work here and then plug it all in on Desmos all at once. It does look like the negatives, negative divided by negative, will cancel out, so I'll get rid of those. Next up, to cancel out e, we do ln on both sides. And you could have done this part on your calculator, but again, I'm going to hold off because I don't want to keep switching. So we get negative 2k equals ln of 225 divided by 257. The final step to solve for k is to divide by negative 2 on both sides. Thus we get k equals the result of this calculation. So let's pop over to Desmos and do it. So in Desmos we get functions miscellaneous ln 225 divided by 257. Whoa, I missed a division sign. 225 divided by 257. Close parentheses. Oops. Close parentheses. All divided by negative 2. We get 0.0665. So we have part A done, k equals 0.0665, which is great. So what that lets us do is it lets us write an equation for the temperature of the turkey after any number of hours. And that's very simple. We just go back to the original problem here. It looks crazy, but our formula is going to be big T, the temperature after any number of hours, is equal to the temperature of the oven, 325, minus the initial temperature of the turkey, which was 68 minus 325. But since we've already done that, I know that the result of subtracting T0 minus TA is just going to be the negative 257 that we got as we worked the last problem. So minus 257 e to the, now we know k, so we have the negative sign from the formula, k is 0.0665, t is t. So we're done with part B. For part C, we need to know the temperature of the turkey at 3 p.m. So 3 p.m. is a trick here. You have to remember you put the turkey in at 8 a.m. So from 8 a.m. to 3 p.m., that's 7 hours. So lowercase t for part C is going to be 7 hours. So we get big T is equal to 325 minus 257 e to the negative 0.0665 times 7. And you can plug this all in on your calculator on the right-hand side because that's all numbers and functions. The key to remember is you're going to have to use parentheses there. So let's see if we can do that. So we get 325 minus 257 e to the parentheses negative 0.0665 times 7, close parentheses, 163.65. And I think that looks good, but we were supposed to round it to the nearest degree, so it should have been 164 degrees Fahrenheit. All right, 3 parts of this problem. It's a tough one, but I think we got it. For part 2, this will not be appearing on our test tomorrow. I've made the choice to edit this out of the problem set, so we'll go over this in the next unit. We had a number of newish topics today, so I don't want to overwhelm you guys. For number 3, a house purchased 5 years ago for $100,000 was sold for $135,000. Assuming continuous exponential growth, hey, that sounds important. Approximate the annual growth rate to the nearest percent. So it looks like in our formula, because it's continuous, we'll be doing A of t equals P e to the RT. We know that because it's continuous. So the value of the house is $135,000. The principal is the starting value, 100,000. E is E. R, that's what we're trying to find, the approximate annual growth rate. We'll leave as a question mark. And T, we have 5 years elapsed in between. So now to solve this, we do division by 100,000 on both sides. That gives us 1.35 equals e to the 5r. Next step to solve for r, we do ln on both sides. That becomes ln of 1.35 equals 5r. Last step to solve for r, we divide by 5 on both sides, and we get r is equal to, let's see if this works. ln 1.35 divided by 5. Why does that seem different from what I wrote here? Sorry. Oh no, it's the same. So 0.06. And that's a trick answer because they want it to the nearest percent. So whenever we use a formula, r is going to be the decimal version of that formula. And we really want the percent version of r from our formula. So we turn r into a percent by moving the decimal 2 spaces to the right. And we get r equals 6%. Fantastic. Last problem here Seth's parents give him $5,000 to invest for 16th birthday. Damn, I wish I was Seth. That sounds awesome. He is considering 2 investment options. Option A will pay him 4.5% interest compounded annually. Doesn't say continuously. That's important. Option B will pay him 4.6% compounded quarterly. Okay? Write a function for option A and B. So the most important part here is this is yearly. Oh, sorry, it says annually. That means the same thing as yearly. Option B is quarterly. And neither of them is continuous. So we're going to be using the older method, the discrete formula for both of these. So it looks like the amount that he'll have in his account for option A of t, is equal to 5,000 times 1.045 to the tth power. Done with that. For quarterly, what that means is Seth is going to be getting 4.6% a year, but we're going to split it into 4 chunks so you can get a piece of that 4.6% every quarter. So we do 4.6 divided by 4, and that becomes 1.15. So this is the yearly percent. We divide it by 4, and that gives us the quarterly percent. Next up, we have to convert this to the decimal version, but before doing that, if we're increasing by this percent every quarter, we'll do 100% plus 1.15%. These give us 101.15%, which becomes 1.0115 as a decimal version. So A of t is equal to 5,000 times 1.0115 to the, not tth power, because this is quarterly, we're getting it 4 times per year, which means 4 times as frequently. So our exponent is going to be 4 times however many years we wait. Now we got Seth's 2 formulas, and I think you can figure out for problem B which option Seth should pick. Alright guys, I'll see you in class tomorrow. You've got your test. I hope this helped. I'm glad